Okay, so today we're diving into something pretty fundamental in AI. We're always talking about making AI smarter, more capable, but what about making it smarter in a way that we can actually understand? Like, how do we build systems that are safe and make decisions that, well, make sense to us humans?
Yeah, that's the core of it. I mean, think about it. When you use like a virtual assistant or you see a self-driving car on the road,
Yeah.
you're kind of building a mental model in your head of how that AI works, right?
Know what
How to do next.
Trying to anticipate it, yeah.
Exactly. But the thing is, a lot of times our human expectations and how the AI is actually programmed to act, they don't always line up. And that gap, that mismatch, is where things can get a little messy. You start to lose trust, you get confused, and in some cases, it can even lead to dangerous situations.
Especially if that AI is controlling something in the real world, like a robot arm on a factory floor.
Exactly. So that's the challenge this paper tackles head on. It's called a Safe Explicable Policy Search, or SEPS for short. And it's a new approach that combines safety and they call it explicability.
Making sure the AI does what it's supposed to do, but also in a way that we humans can follow along with.
Exactly. And they test this all out, not just in simulations, but also with a real world robot. So that's what we're going to unpack today. What is SEPS? Why is it a big deal? And what might it mean for the future of, well, how we interact with AI?
Let's jump right in. So they call it Safe Explicable Policy Search, right? This SEPS thing. Can you break that down a little bit? What exactly are we searching for?
It's all about training AI agents. You can think of an agent as like a little AI brain that controls something, maybe a robot, maybe a software program. And this policy, it's basically the set of rules the AI uses to decide what to do in any given situation. So it's like, if this happens, do that. If that happens, do this.
Okay, so it's like the AI's game plan.
Exactly.
Yeah.
But here's the twist. In SEPS, we're not just looking for any policy. We want a policy that's both safe and, well, explicable.
Yeah.
And they frame this as a constrained optimization problem.
Constrained optimization. That sounds a little academic.
Yeah, it can be a bit jargony. So think of it like this. The AI has a goal, right?
Yeah.
Like navigating a robot across a room, baby. That's the optimization part, finding the best way to achieve that goal. But there are some rules it has to follow, some boundaries. Those are the constraints.
Like, don't bump into the furniture.
Exactly. And in SEPS, those constraints involve safety, like avoiding obstacles, but also a certain level of performance on the task itself. Like, you can't be so focused on being safe that it takes forever to actually reach its goal.
So it can't be super cautious and slow.
Right. And then here's the really interesting part. They also build in this constraint that the AI's actions have to be explicable, meaning they should align with what a human user would expect to see.
So it's not just about being safe and efficient. It's also about being understandable to us humans who are watching it.
Exactly. And SEPS does all of this by bringing together two really cool areas of research: constrained policy optimization, or CPO, and explicable policy search, or EPS.
Okay, so CPO and EPS.
Yeah, so CPO is really good at making sure the AI stays within those safety and performance boundaries, kind of like keeping it on the right track. And EPS is all about learning from user feedback to figure out what actions make sense to a human observer.
So like, if a human sees the AI doing something unexpected, it can adjust its behavior.
Right. It's a learning process. And they actually tested SEPS not just in those kind of virtual simulated environments, but also with a physical robot arm to see how well it works in the real world.
So they put it to the test, huh? And what did they find? Did it actually work?
Yeah, they found that SEPS was actually really good at learning these behaviors that were simultaneously safe. They didn't violate any of those rules, understandable to humans watching it, and still effective at completing the task. Like, it wasn't sacrificing performance just to be safe or explicable.
That's pretty impressive, I have to say. So it really seems like a step towards making AI more trustworthy, more reliable partners for us humans.
Exactly. Because that's the key, right? If you can't understand how an AI is making decisions, it's hard to trust it, especially if it's in a safety critical situation. Like, imagine a self-driving car that suddenly makes a sharp turn for no apparent reason. Even if it's technically the optimal maneuver, you'd probably be pretty freaked out as a passenger.
Yeah, that makes sense. It's like, even if it avoids an accident, you'd still be like, what the heck was that about?
Exactly.
Yeah.
And so the idea behind SEPS is that to build really effective human AI teams, the AI needs to act in a way that aligns with our expectations. It needs to be predictable, transparent, understandable.
Right, so we can kind of anticipate what it's going to do, and we're not constantly caught off guard.
Exactly. And the researchers, they point out that this whole idea of explicable planning, has been around for a while, but it often hasn't taken safety into account as rigorously as it should. Like, you can have an AI that's really good at doing what a human expects, but it might accidentally do something dangerous in the process.
Yeah, I can see how that could be a problem.
Right. So SEPS addresses this by incorporating those safety constraints directly into the learning process. They even contrast it with some earlier work, like this thing called Safe Explicable Planning, or SEP. And SEP was a good step, but it was mostly designed for these very specific scenarios where you had a limited number of possible actions and you kind of already knew how the human and the AI were thinking.
Which is not very realistic for most real-world situations.
Right. Like, the real world is messy, there are tons of possibilities, and every human thinks a little bit differently. So SEPS, it goes beyond that. It can handle these more complex environments with a continuous range of actions. And crucially, it can actually learn about the user's expectations from feedback, rather than assuming it already knows everything.
Well, it's pretty clever. So it's like it observes how humans react to its actions and then uses that information to figure out what makes sense to them.
Exactly. And they illustrate this really well with this example of a car merging onto a highway.
Oh, yeah, I remember that from the paper. It's a good way to visualize it.
Yeah, so imagine you have this autonomous car trying to merge onto a busy highway. The AI, it might have its own internal idea of the optimal way to do that. Like, maybe it waits for a huge gap in traffic to make a really smooth, energy-efficient merge.
Like the AI is being super cautious.
Right. But a human driver, they might have different expectations. They might expect the car to be a little more assertive, maybe edge forward and take a smaller gap, prioritize getting onto the highway quicker.
Like a human driver might be a little bit more impatient.
Exactly. And so a purely optimal behavior might not align with those human expectations. And conversely, if the AI just blindly tries to do what a human expects, it might end up doing something risky, like cutting someone off.
Yeah, that's not good.
Right. So SEPS, it aims for this middle ground. The safe, explicable behavior in this case might be to merge a little more assertively than the purely optimal strategy, kind of aligning with that general human expectation of a timely entry onto the highway, but still adhering strictly to all the safety protocols, like maintaining a safe distance, not making any sudden jerks.
So it's like finding that sweet spot where it's both efficient and understandable to the human drivers around it.
Exactly. And the way SEPS actually learns about those human expectations is through this thing called a surrogate reward function, or EDH. It's basically a learned representation of what the user seems to value or expect based on their past reactions.
So it's like the AI gets a little reward signal when it does something the human approves of.
You got it. Now, you might be thinking, why not just use a standard constrained Markov decision process, or CMDP, to solve this? And CMDPs, they're really good at optimizing for a goal under certain constraints. But the tricky part here is that the explicability goal, it's tied to the user's perception of the world, which might be different from the AI's actual understanding of the world.
Right, because the AI has access to all this sensor data and internal models, while the human might be making assumptions based on what they can see.
Exactly. So SFPS, it gets around this by doing something really clever. Instead of trying to combine the explicability goal with the AI's main task objective directly, which can be really messy and involve a lot of fine-tuning, it sets a minimum level of performance on the main task as a hard constraint.
Like a baseline. It has to at least achieve this much on its main job.
Exactly. And then within those boundaries, it tries to maximize the probability of taking actions that the user would expect, based on that learned H function. So it's like, I got to do my job well, but within those limits, I'm going to try my best to make sense to humans watching me.
That makes a lot of sense. So the paper mentions that they use constrained policy optimization, or CPO, as kind of the foundation for this. But standard CPO usually deals with just one constraint. How does SEPS handle having multiple constraints, like both safety and that minimum task performance level?
Yeah, so that's one of the key things they figured out. They came up with this analytical solution, especially for the case where you have two constraints, which is pretty common. And that solution, it's a way to efficiently update the AI's policy, its way of behaving, while still respecting all those constraints.
So it's not just randomly trying things. It has this mathematical framework to guide its learning process.
Right. Now, we talked about this explicability score earlier, and in the paper, they describe it as the negative kale divergence of trajectory distributions, which, that's a mouthful.
It sounds pretty technical.
It is. But essentially, think of kale divergence as a way to measure how different two probability distributions are. So in this case, it's comparing the set of possible future actions and states that the AI thinks might happen based on its understanding of the world, with the set of actions and states that the user expects based on their mental model, which we're approximating through that H function.
So it's like, how much does the AI's prediction of what's going to happen differ from what the human thinks is going to happen?
Exactly. And by minimizing this kale divergence or maximizing its negative, which they call the explicability score, the AI is basically trying to make its behavior as statistically similar as possible to what the user anticipates.
So the lower the kale divergence, the higher the explicability score, the more predictable the AI's actions are from the human's perspective.
Exactly. Now, another important concept here is the distinction between the AI agent's own internal model of the world, which they call MA, and the user's belief about how that agent works, which they call MHA. The agent's model, it's a CMDP, right? It has its own goals, its own reward function, and those safety constraints it has to follow. The user's belief, it might be a lot simpler. They might not know all the details of how the AI works. And that difference is what can lead to those expectation mismatches.
Right. So the AI might be thinking about all these complex factors, while the human is just like, well, I think it should go this way.
Exactly. And that's why SEPS is so powerful, because it doesn't just try to optimize for one or the other. It takes both perspectives into account. And by setting that minimum performance level as a hard constraint, it prevents the AI from becoming too obsessed with being explicable at the cost of actually doing its job well.
Right, because ultimately we want AI that can both perform its tasks effectively and be understandable to us humans.
Exactly. So how does all this relate to the broader field of explainable AI or XAI? Well, SEPS makes a really important contribution to the area of XAI that's focused on generating AI behavior that is inherently understandable. Like you have these concepts like legibility, which means you can understand what the AI is trying to do just by watching it, and predictability and transparency. And SEPS, it brings all these together by directly addressing safety within this explicable planning framework.
So it's not just explaining what it did after the fact, it's actually trying to act in a way that makes sense from the get-go.
Exactly. And it does all of this in a way that allows the AI to learn about human expectations directly from feedback, without needing some pre-programmed model of how every human thinks. So it's a really big step forward in terms of both the theory and the practical applications.
Yeah, it seems like a very powerful framework. Now, the paper goes into some really interesting evaluations in different environments, both simulated and real world. Let's dive into those a bit. The point goal environment, where they had this conflict between what the user expected and a hidden safety rule, that one was particularly illuminating.
Yeah, so in point goal, the agent, it had to navigate to a specific point. And there were these vases that were visible, so the human user would naturally expect the AI to avoid them. But then there were also these hidden hazardous areas that the user couldn't see, and the AI had to avoid those too for safety reasons.
So it's like the AI knows something the human doesn't.
Right. And so the purely optimal strategy for the AI, in some cases, it involved taking paths that were pretty close to those vases. And that makes sense from the AI's perspective, because it knows about those hidden dangers. But from the human's perspective, it looks like the AI is being reckless.
Right, because the human is like, why is it getting so close to those vases?
Exactly. And so the approaches that just focused on meeting user expectations or just tried to balance those different objectives, they often ended up with the AI wandering into those hazardous areas, which is obviously not good.
Yeah, that violates the safety constraint.
Right. But SPS, it was able to navigate this really well. It learned to avoid those hazardous areas, so it was respecting that hidden safety constraint, but it also chose a path that stayed further away from the vases, even though it was a slightly longer path. And that's because it had learned from user feedback that humans generally expect robots to avoid fragile objects.
So it was able to kind of reconcile those two potentially conflicting goals?
Exactly. And it did this better than the other methods they tested, which either didn't explicitly handle safety or didn't take user expectations into account in the same way.
That's really cool. And then they also tested it in this point button environment where the human expected the AI to press buttons along the way, even though its main goal was just to reach the target efficiently.
Yeah, that one's interesting because it highlights this tension between what the user might expect and what's purely optimal for the AI. So in this environment, the AI's main goal was to reach the target as quickly as possible while avoiding these little gremlins that were moving around.
Sounds like a video game.
It kind of is. And the user, they had this expectation that the AI would press these buttons along the way, even though pressing the buttons didn't actually help the AI reach the target any faster.
So it's like a purely optimal AI would just ignore the buttons and go straight for the target.
Exactly. And the approaches that just focused on maximizing the AI's reward or just focused on satisfying the user's learned preferences, they didn't do very well. They either ignored the buttons completely or took these really roundabout paths to press all of them, which made them really inefficient.
So they were either too optimal or too explicable.
Right. But SEPS, it found this nice middle ground. It managed to press at least one of the buttons along the way, so it partially satisfied the user's expectation. But it still headed in a reasonably direct path towards the target, avoiding the gremlins. And that's because it was able to balance those different objectives as constraints within that CMDP framework.
Yeah, it seems like that constrained optimization approach is really key here. It's not about completely sacrificing one goal for another. It's about finding the best solution within those boundaries.
Exactly. And then to really bring this all home, they tested SEPS with a real physical robot arm, this UR5 robot, in a task where it had to set a table. And this is where you really see the practical implications of this whole framework.
Yeah, because now it's not just moving around in a virtual environment, it's interacting with real objects.
Right. So in this scenario, the robot had to place a cup near the user, but there was this glass in the way. And if the robot just went straight for the cup, it would have knocked the glass over.
Which is obviously not what you want in a table setting robot.
Right. So the robot's own optimal way of placing the cup safely, it wasn't necessarily where the user intuitively expected it to go. And if the robot just blindly followed the user's expectation, it would have caused an accident.
So I had to do something a little bit more clever.
Exactly. And the approach that just focused on explicability, it managed to move the glass and then place the cup, but it was kind of inefficient. It took a lot of steps. But SEPS, it found this really elegant solution. It first nudged the glass out of the way, gently and safely, and then placed the cup near the user.
So it was both safe and understandable to the human observer.
Exactly. And it did all of this more efficiently than the other methods they tested. So this experiment, it really shows the potential of SEPS to generate robot behavior that's not just safe and effective, but also aligned with human expectations in a way that makes it a more trustworthy and intuitive partner.
It's really exciting to see this kind of research pushing the boundaries of what's possible in human-AI interaction. Now, as we like to do, let's shift gears a little bit and go into our novel notions segment. We've seen how SEPS can learn these safe and explicable policies from user feedback. But what if we took these ideas even further? Where could we go from here?
Yeah, that's where things get really interesting. So one idea that comes to mind is, what if the AI could anticipate potential misunderstandings before they even happen? Right now, SEPS, it kind of reacts to feedback after the fact. But what if it could be more proactive?
Like it senses that the human might be confused and then adjusts its behavior accordingly.
Exactly. So imagine an AI that can generate multiple possible actions, and then before actually doing anything, it tries to gauge which of those actions the user is anticipating. And it might do this by analyzing subtle cues in the user's behavior, or even by asking a quick question if the situation allows for it.
So it's like, hey, I'm thinking of doing A or B. Which one seems more like what you're expecting?
Yeah, something like that.
Yeah.
And this could be especially valuable in really complex dynamic environments where even a small misunderstanding could have big consequences. Like imagine collaborative robots working alongside humans in a busy warehouse, or even advanced driver assistance systems in really unpredictable traffic situations. Being able to anticipate those potential misunderstandings, it could make those interactions a lot smoother and safer.
Yeah, it could prevent those moments of like, wait, what are you doing?
Exactly. And this idea, it builds on that existing feedback loop in SEPS, but it adds this layer of proactivity.
Yeah.
And it connects with some really interesting research in areas like anticipatory planning and human-robot communication.
It's like giving the AI a little bit of social intelligence.
Yeah, exactly. Now, another novel notion that I think is really intriguing is the idea of personalized explicability profiles. So right now, SEPS, it kind of aims for this generally explicable policy based on feedback from, an average user. But we know that different people have different mental models, different levels of expertise, different preferences.
Right. Like my grandma probably expects a robot to behave differently than I do.
Exactly. So what if we could develop these personalized explicability profiles for each individual user? The AI could for its behavior to be maximally explicable to the specific person it's interacting with.
So it's like it knows how you think and then adjusts its behavior to make sense to you specifically.
Right. And this personalization, it could go beyond just choosing different actions. It could also involve executing the same action in a slightly different way, or even providing a brief explanation if the interface allows for it.
So it's like it speaks your language, both literally and figuratively.
Exactly. And this aligns with some of the bigger trends in AI right now, like personalized AI and adaptive systems. And it could draw upon techniques from user modeling and preference learning. And the potential benefits are huge. Like imagine personalized AI assistants that really understand your individual needs and preferences, or autonomous vehicles that can adapt their driving style to each passenger, or even educational AI tutors that tailor their explanations to each student's learning style.
It really opens up a whole new world of possibilities for making AI more intuitive and more human-centered.
Absolutely. And I think that's the key takeaway here. These are just a couple of ideas, and there are probably many more out there.
Yeah.
But what CPS has done is it's laid the groundwork for a whole new approach to building AI that's not just intelligent, but also understandable and trustworthy.
It's not just about making AI smarter, it's about making it smarter in a way that works for us humans. Well, this has been a really fascinating deep dive. And for those of you listening who want to go even deeper, we highly encourage you to check out the original research paper. We'll have a link to that in the show notes.
Yeah, definitely give it a read. It's a really well-written paper, and it lays out all the technical details in a very clear way.
So to wrap things up, I think the big question we're left with is, as we continue to develop more and more sophisticated AI systems, how will these advances in safe and explicable AI shape the future of our interactions with them? How will it change the way we work with them, learn from them, trust them?
That's the million-dollar question, isn't it?
Yeah.
And I don't think anyone has the answer yet. But I think it's a question worth pondering as we move forward into this exciting new era of intelligent machines.
Absolutely. Well, thank you so much for joining us on this deep dive. We'll see you next time.
Thanks for having me. It's been a pleasure.